Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about the network theorems, and in the network theorems, we are going to discuss about Millman's and compensation theorem. Previously, we have discussed various network theorems like superposition and Norton's, Thevenin's and maximum power transfer theorem. So here in today's class, we are going to discuss about the Millman's and compensation theorem. So here this Millman's theorem is also called as the parallel generator theorem. So when coming to the statement for this Millman's theorem is, of course here the common thing is every network theorem is applicable only for the linear and bilateral elements, okay, or the network, linear and bilateral networks. So here the Millman's theorem states that when a number of voltage sources are in parallel having with their internal resistance respectively, or the number of current sources are in parallel having their internal resistances respectively, the arrangement can be replaced by a single equivalent voltage source in series with an single equivalent resistance or the current parallel with an equivalent resistance, which means here, which is also some kind of similar to the Thevenin's theorem, but here the difference is there. The Thevenin's, the procedure to follow or the procedure to calculate the Thevenin's theorem is different. The Thevenin's voltage or Thevenin's resistance is different, and here the same the voltage, the equivalent voltage or the equivalent resistance, or the procedure to find the equivalent voltage and the equivalent resistance is different. So which means here by considering one simple example, so we will understand better. So here let us consider this circuit having some n number of the various number of voltage sources, okay, and are in the voltage sources are parallel with each other, and the voltage sources are having their internal resistance in series with that particular voltage source. So which means here let us consider here V1, V2, V3 are the three various voltage sources, and here R1 is the internal resistance of the V1, and R2 is the internal resistance of V2, and similarly here R3 is the internal resistance of the V3. Then according to this compensation theorem, let us consider here RL is the load resistance. So suppose if you want to find the current flowing through this load resistance by using the Millman's theorem, so here similarly, if you are having a current sources or which are connected in parallel again. So as we know, the internal resistance of the current source is connected in parallel with that particular source. So here R1 is the internal resistance of the current source I1, and R2 is the internal resistance of the current source I2, and R3 is the internal resistance of the current source I3. So then here also let us consider here RL is the load resistance. Then if you want to find the current flowing through the internal resistance RL. So here if you want to find the current flowing through the internal resistance RL, so here these two are the different circuits, because in the circuit 1 which is having only the voltage sources which are connected in parallel, and here these are the current sources, and the current sources also connected in parallel to the load resistance. Then now we are going to find the current flowing through the load resistance by using the Millman's theorem. So according to Millman's theorem here, as you can see the statement, the number of voltage sources are in parallel having with their internal resistance, okay, because here you can see the number of voltage sources are in parallel having their internal resistance R1, R2, R3 respectively, or if the number of current sources are parallel having their internal resistance, okay, then these circuits can be replaced by a single equivalent voltage source in series with the equivalent resistance, which means here like this. So here the voltage sources V1, V2, V3 and so on are replaced with the single voltage source. Let us consider here it is V in series with the equivalent resistance. So the internal resistance, okay, the equivalent resistance of the internal resistance which is R, okay, in series with the load resistance RL. This is if you replace this with like this. Then similarly here, if you go for the current sources are parallel, then this circuit can be replaced with the like, okay, so here as you can see, the current source and current source in parallel with the equivalent current source and the equivalent resistance and the load resistance all are connected in parallel. So then already we know how we can find the current flowing through these particular circuit or the and the current flowing through these RL by using here, of course, by using the voltage division rule. You can find the voltage across the RL, and the I means here I is equal to, let us consider I is equal to, which means the current flowing through the load R IL, which is equal to V by R plus RL. And here by using the current division rule we can find, right? Then how to find these V and R here, that is also very important, because here this circuit is something looks like the Thevenin's equivalent circuit, but here this V is not the Thevenin's voltage, and R is not the Thevenin's resistance, right? So here the procedure to calculate the V and R are different from the Thevenin's theorem. So then how to find the V here? So the V that we can find is V1 by R1 plus V2 by R2 plus V3 by R3. Okay, in this way we can find the V, and here R is the R equivalent. R equivalent is equal to 1 by R1 and 1 by R2 plus 1 by R3. Okay, so 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So in this way we can find the values of V1 and I1. So to get better understand here, I am going to consider one example. So here calculate the current through the 3 ohms resistor using the Millman's theorem. So which means here here it is the 3 ohms resistor. So we need to find the current flowing through this 3 ohms resistor, right? So what we need to do then, by to apply the Millman's theorem, then we should just replace this the circuit into an equivalent circuit, okay, or we can also call as Millman's equivalent circuit. So that equivalent circuit is consisting of one voltage source, one resistor and one load resistor, right? So now here in this circuit the variables are, we don't know the V and R values, so now we need to calculate the values of V and R. So now we need to calculate the V and R. So first of all let us find the R value. So here 1 by R which is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. So of course here let us consider here R1 is equal to 12 ohms and R2 is equal to 6 ohms and R3 is equal to 4 ohms. Then substitute these values in this equation. So here and again V is equal to, as we know just now we have discussed, V1 by R1 plus V2 by R2 plus V3 by R3 into R equivalent, right? Then substitute the values here. So 1 by R is equal to 1 by R1, which is R1 is equal to 12 ohms, and 1 by R2, and R2 is 6 ohms, and 1 by R3 is 4 ohms, and if you simplify then you will get 1 by R is equal to 1 by 2. Then R is equal to 2 ohms. So here this is the R is equal to 2 ohms. Then now we need to find the V value. So for that here V is equal to 6 by 12 of course here as you can see V1 by R1 plus V2 by R2, of course here the V1 having the polarities of plus minus, but V2 is having the let us consider here it is V1 and here it is V2 and here it is V3, right? So here V1 is plus and minus polarities, but V2 is opposite polarities with respect to V1, and V3 is also same polarities with V1. So that's why here V1 by R1, so V1 is equal to 6 by R1 is the 12 volts, so 6 by 12 minus, because here the opposite polarity is minus V2, here V2 is the 3 volts and R2 is the 6 ohms, so V2 by 6, this is 6, V2 by 6, plus V3 by R3, so V3 is again here it is 10 volts and R3 is equal to 4 ohms, okay, into R equivalent just now we have calculated into 2, then we will get the V value. So then the value of the V here it is 5 volts. Then we place here the V value also here in this particular circuit. Then now we need to find the current flowing through 3 ohms, because here RL is nothing but here it is 3 ohms. So now by using this equation, okay, just V is equal, the current flowing through the 3 ohms is equal to the total voltage V by and the total resistance R plus the RL, so 5 by 2 plus 3, which is equal to 1 ampere. So this is the simple way to apply the Millman's theorem, or by using the Millman's theorem, we can calculate the current flowing through the any resistance, right? So let us consider another example, which is having only the current source. I mean, the current sources with their internal resistance are connected in parallel. So now here also, let us find the current flowing through the 3 ohms resistor. So here we need to find the value of the I. Okay, I mean, here the equivalent circuit is different than the previous case, because in the previous case those are all the voltage sources which are connected in parallel, but in this case here all the current sources which are connected in parallel. Okay, so then in this case it is something like that Norton's equivalent circuit, right? Okay, so here it is I and R, okay, are connected in parallel with the load resistance RL. Now we need to find the value of the I and the value of the R. So first let us find the value of the R. So here again the procedure is same to calculate the R value like in the previous case. So which is 1 by R, or we can also call it as a R equivalent. So 1 by R equivalent is equal to 1 by R1 plus R2 plus R3 plus and so on. So here how many resistors are there? Let us consider here it is R1 and here it is R2 and here it is R3. Again here also there are 3 resistors are there. Then substitute the values of R1, R2, R3 in this particular equation. Then we will get the value of the 1 by R equivalent. Then here, then to find I value, I is equal to, simply we can make it addition I1 plus I2 plus I3. Of course, here the sign is again depends on the direction of the currents, whether all the directions of the current sources are in the same direction or not. If the same direction, then we simply put the positive sign, and if it is opposite direction, then we will consider one as a reference direction positive, then the opposite should be the negative value, right? So here then 1 by R is equal to, here R1 is equal to 12 ohms and R2 is equal to 6 ohms and R3 is equal to 4 ohms. So 1 by 12 plus 1 by 6 plus 1 by 4, which is equal to 1 by 2. Then R is equal to here also the same value, which is equal to 2 ohms. Then because of course the same circuit and the same resistors are there, okay, only the difference is there it was voltage sources, and here it are here these are the current sources. Now find I value. So I is equal to, here also you can see here the I1 value, I1 direction and I3. Oh, let us consider here it is I1 and here it is I2 and here it is I3. So here the directions of the currents I1 and I3 are same, but the I2 is opposite to the I1 and I3. So that's why here the I1 and I3 are the positive currents, and I2 let us consider as a negative current. So that's why here, so I1 is equal to 0.5 minus I2 is equal to 0.5 plus I3 is 2.5. So 0.5 gets cancelled. Then I is equal to here 2.5 amperes. Then substitute these values of R and I in this particular circuit. Okay. Then here I is equal to 2.5 amperes and R is equal to 2 amperes. Okay. And RL is equal to 3 ohms. Now we need to find the current flowing through this RL. Okay. So which is I, let us consider I 3 ohms. So here I 3 ohms, which is equal to the total current IN is to 2.5. Okay, because this is some kind of the current division rule that we are applying here. So this is the total current I. So let us consider here the current flowing through R is I1 or this is I2. So here I 3 ohms, which is equal to the total current I into the opposite resistor, which is Rn. Okay, let us consider here it is Rn, this is Rn. So Rn by Rn plus RL. Okay, so here IN is equal to 2.5 and Rn is equal to 2 ohms by Rn again 2 plus 3 ohms. Then if you simplify this, then you will get I 3 ohms is equal to 1 amperes. So this is the way to find or to calculate the current flowing through the load resistance by using the Millman's theorem, right? So here let me give you another way. I mean, of course the procedure is same, like we have to replace the given circuit into the equivalent circuit, but the equivalent circuit parameters, which are V and R, we can find in the another way also, that let me tell you. So for that let me consider one more simple circuit, which is having again the 3 voltage sources are connected in parallel with their internal resistances. So here the circuit is like this. So here one resistor and one voltage source, and again here one more resistor and one more voltage source, because only we can apply this Millman's theorem if the circuit is connected in this configuration. Otherwise, we can't apply the Millman's theorem. So here again, let us consider the load resistance. So here let us consider, here it is 20 volts and here it is 40 volts and here it is 50 volts. And the values of the resistors are here 2 ohms and 4 ohms, 5 ohms and here it is 10 ohms, right? Okay, so now by using the Millman's theorem, we are going to find the current flowing through this 10 ohms resistor, okay, I. So first what do we have to do? We have to replace with this circuit with the equivalent circuit. So that equivalent circuit consisting of the equivalent resistance and the voltage, the total voltage with all are connected in series, because here these are the voltage sources which are connected in parallel. So let us consider, here it is V and here it is R and here it is RL. So here we know RL is equal to 3 ohms and now we need to find the current flowing through this RL, okay, I. So then here let us write here V1 is equal to 20 volts, let us consider, and V2 is equal to 40 volts and V3 is equal to 50 volts. And similarly, let me write here R1, R2 values also. R1 is equal to 2 ohms and R2 is equal to 4 ohms and R3 is equal to here 5 ohms. Okay. So now here, let us write here, these are the resistors. Okay. So now the reciprocity of the resistors, let us consider the values are G1. So G1 is equal to, here it is 1 by R1. So which is equal to 1 by 2. And similarly here, Z2 is equal to 1 by R2, okay, so which is equal to 1 by 4. And similarly here, G3 is equal to 1 by R3, so which is equal to 1 by 5. Right. So now in this case also we need to find the value of V and R, right? So here the equation are, what is that? The equation that we can use to find here V is equal to V1 G1 plus V2 G2 plus V3 G3 by G1 plus G2 plus G3. Then substitute the values here. Okay. So here what is the value of V1 here? V1 is 20. So 20 into, here G1 is 1 by 2 plus here V2 is 40 into G2 is 1 by 4 plus, and again here V3 is 50 into here G3 is 1 by 5 by here 1 by 2 plus 1 by 4 plus 1 by 5. So here, of course, here you will get cancelled. Okay. So in the numerator that you will get here, it is 10 plus 10 plus 10 by here 1 by 2 plus 1 by 4 plus 1 by 5. Then if you simplify this, then V is equal to V is equal to 60 by 19. Sorry, 40 by, yeah, 60 by 19, because here, no, it's not 60, 600 by 19 that you will get. Okay. So then, now calculate the R value. So here R is equal to, as we know, 1 by G1 plus G2 plus G3. So which is equal to, so here 1 by G1 is 1 by 2 plus 1 by 4 plus 1 by 5. So which is equal to 20 by 19. Right. So then now, of course, the circuit is like this, plus minus, and here it is RL. So here it is RL and here it is R value and here it is V value. So substitute here. So here R is equal to 20 by 19 and V is equal to, then IL is equal to V by R plus RL. So here V is 600 by 19 that we have calculated, by here R is equal to 20 by 19 plus 10. Then finally you will get here this is 60 by 21, so which is equal to 2.87 amperes, which is IF. So this way also we can find, right? So but of course here this what is that, V is equal to V1 G1 plus V2 G2 plus V3 G3 by G1 plus G2 plus G3. Okay, this is also we get from the same previous equation, just for the simplification purpose only, or the other way that we can use for that purpose only I have explained this problem. Now we are going to discuss about the compensation theorem, right? So here first let me give the circuits also. So by using these circuits we can get understand clearly, right? So, then the compensation theorem, it states that in a linear time invariant network, when the resistor RL of an uncoupled branch, okay, the resistor RL of an uncoupled branch carrying a current I is changed by delta R, okay, is changed by delta R, then the current in all the branches would change and can be obtained by assuming that the ideal voltage source has been connected such that VC is equal to I into delta R in series with the RL plus R delta when all other sources in the network are replaced by their internal resistances. Which means, suppose here this is the, let us consider this is a network, okay, the first network, and the first network let us consider here RL means this is the RL, and the current flowing through the RL is equal to I, let us consider, right? Then suppose the current I, okay, because here like this, like the current I is changed by delta R. So which means suppose here the current I is the current flowing through the RL. Suppose if you place an extra resistor which is called as a delta R here, so something like that in series with this RL. Okay, of course anyway if you are connecting extra resistance in series with this RL, then the current flowing through the RL will definitely change. So let us consider here the change in the current. Let us consider here it is I dash. Okay, so that means then the current in all the branches would be changed and can be obtained by assuming. Then here this I dash which is equal to, okay, so when the circuit is replaced with the voltage source, okay, the circuit, okay, our voltage source VC which is equal to I into delta R. So here I is the actually the current flowing through the RL before connecting the delta R. I into delta R, whatever the what is that the change in what is the resistance that we have placed here into delta, I mean into R delta, okay, I into R delta. So then here now I delta current is equal to I minus I dash. Okay, so to better understand here, let me take one example here. Okay, so yeah, as you can see now here, this is the set, I mean now here let us consider here it is I. Of course if you place some resistor in series with this RL, definitely the current flowing through this RL will change. Let us consider the change in the current, okay, or the variable current is I dash, right? So here then if you replace this VC is equal to I into delta and delta I and this thing, then here the current flowing through this, I mean this I and the current flowing through now, okay, we have changed, okay, and this case is same, okay, the current flowing through here I is same. Then here let us consider one example to better understand this compensation theorem. So here let us consider here 4 ohms is the RL, right? So then the current flowing through these 4 ohms is, let us consider I. Now we are just adding some more resistance, let us consider which is R delta, so 3 ohms. Now find the current flowing through, I mean of course here it is, let us consider here it is I and here it is I dash. So now find the current flowing through I and I dash, right? So how we can find the current flowing through I and I dash? So just apply the loop analysis, okay, or any other way that we can find. So here we are applying the loop analysis. So let us consider here these are the two loops and write the loop equations. Okay, and by solving these two equations, then you can find the current values. Okay, so here I1, which is the current flowing through the first loop, is 2.273 amperes, and here I is equal to 1.36, which is the current flowing through the 4 ohms. Then similarly, find the current flowing through this, this I dash, the current flowing through these 4 ohms in the second circuit. So here also similarly, let us apply the mesh analysis. Okay, so here also write the mesh equations, and by solving these two mesh equations, then we can get I2 value and I dash value. Of course, here I and I dash value both are different. Now the thing is, now we should replace here, okay, the circuit, in that circuit now we should replace these what is the load as a voltage source. Okay, that voltage source value V is equal to I into delta R. So we know what is the value of V, which is here what is the value of I, that is here 1.36 into the delta that we are considered is 3 ohms. Then here the value of the V should be 1.36 into 3 ohms. And here the resistance that we should consider is the total resistance, which means the actual load resistance plus the extra resistance that we are added in series with that load resistance, which is 3 ohms. So which means now we should add here 3 plus 4, so which is 7 ohms. Now find the current flowing through this particular case. Okay, let us consider here it is delta I. So of course here V is equal to 4.092 because here I is 1.36 that we have considered from here, and here 3 is delta R, so delta R is from we are taking from here, right? So now the delta I value that you can find here it is by using again the same analysis. So the delta I is equal to 0.481. Of course, anyway you will get the different value. Now, okay, so now here, of course, here the same circuit that we have considered. Okay, so here we got the value of 1.363, and if you consider, okay, and if you just consider this circuit, okay, so in this circuit also you will get the I value as the same like here, that is 1.367. So for that, let us see. Okay, so again apply the mesh analysis. Okay, so this is the mesh analysis, right? Okay, then here you got I is equal to 1.363. Because the difference between these two circuits is here, the all other voltage sources are replaced with the short circuit and current sources are replaced with the open circuit. Okay, so and here from here also you can simply calculate the I value. Okay, so here I is equal to I delta plus I dash. Right, so I delta is 0.48 and I dash is 0.82. If you add these two values, okay, then you will get the I value as a 1.38. Or in another case, you just what is the difference between these two? Here the difference between these two is we have replaced with this and we have replaced with this. Okay, so then find the current flowing through this particular branch again. Okay, so here it is 1.363. So here this current and this current are same. So that is what the Millman's theorem states. So in the next class we will discuss the same these compensation and Millman's theorem with the input as a AC voltage. Right? Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.